Let's quickly do a video of example 1. This is problem number 35 from section 5.2 from Neuhauser. And here we have this function, they call it a formula, x of f equals cf to the gamma. And we're assuming that c is a constant, and so is gamma. Gamma is also a constant. And f is the number of flowers on a plant. X of f is the number of pollinator visits based on the number of flowers. So a couple things you just want to take note of is that we're going to assume C and F are greater than 0, or else it just wouldn't make any sense, right? We don't have a negative number of flowers on a plant. That doesn't make any sense. And so F is going to be greater than 0. And then if C were negative, then the number of pollinator visits would be negative, and that wouldn't make any sense. Okay, so we're just going to assume that. Also assume gamma is a constant, and what we're interested in finding is we want to see that the average number of pollinator visits increases with the number of flowers F, but the rate of increase decreases with F. So what is going on here? We want to find gamma, or I should say find values of gamma such that the following hold. And I'll write the words such that x prime of f is greater than 0, but x double prime of f is less than 0. Right? And x prime of f being greater than 0 just corresponds to this yellow highlighting right here, and x double prime being less than 0 corresponds to the green highlighting right there, okay? So that's what we're going to do. So what we're going to do is we're just going to take the derivative, remembering that c, and again, gamma is constant. I know we're solving for gamma, but when we differentiate with respect to f, we treat gamma as a constant, okay? So let's just go ahead and do it. So first off, note that x prime of f equals c gamma f to the gamma minus 1, right? This is a power rule, right? This is a power rule. Now, I guess I'm assuming that gamma does not equal 0. Let's go ahead and see why. In fact, let me even move this down a little bit. Let me just write in red over here. Gamma does not equal 0. For if it did, let's just see. If gamma equaled 0, then we would have x of f equals c f to the 0, which equals c, a constant. Then x prime of f equals 0. And do you see that that already violates this condition right here? So let me just highlight that in yellow, which is, and like no good. Okay? So gamma does not equal 0. And so now when we take the derivative, the first derivative, we can do the power rule, and we know it's going to be like this. Okay? All right, now another thing to note here. Actually, let's go ahead and take the second derivative as well. And maybe with one further note, if gamma equals 1, well, then what's going to happen here? Then x prime of f is going to equal c gamma f to the 1 minus 1, which equals c gamma. And that actually is greater than 0. So actually that could be okay. Actually, if gamma equals 1, it would just be that, right? So it would really just be c, a constant. And that looks like it could be okay, right? Except because just to point out, C is greater than 0, which is what we're looking for. The problem is x double prime of f, again, at this point, will equals, I shouldn't say again, but will equal 0. And do you see that that violates the condition we were looking for with the other green highlight, right? This guy right here. So, again, not okay. So gamma does not equal 1. Okay? All right, so back to our differentiation. Okay, so we have this guy. We're just going to keep that in mind. And then we're also going to take the second derivative. X double prime of f is going to equal c gamma minus 1 f to the gamma minus 2. And we can do this because we've ruled out the possibility of gamma being 1 or 0, right? So we can just use the power rule. It just works like that. All right, now let's think about this. Let me actually go ahead and move this guy down here and this guy down here. We want this guy to be greater than 0, and we want this guy to be less than 0 for choices of gamma, okay? Well, let's make a couple of observations. Actually, maybe I'll move this over to the left here, okay? So, observation number 1 is that, let's see how we would put this. Note that C and F to the, yeah, so note that C and F are greater than 0, right? Right, again, whoop. Sorry about that. Weird. We will, that again. C and F are greater than 0, and that implies that C times F to the gamma minus 1 is greater than 0. Right? By the way, where are we getting this assumption from? We're getting it from right here. Right? We assumed that C and F were greater than 0, okay? Okay, so why does that matter? Well, it means that if we want this to be true, then gamma has to be greater than 0. Right? Because if this is greater than 0 and that's greater than 0, then I'll use another color. This guy also has to be greater than 0 in order for this to hold. Okay? Now, let's try to use similar reasoning for x double prime. Okay? Again, we have C, and I guess now we have that gamma and F are greater than 0. Again, these two guys are by assumption. This guy is by what we just showed. Okay? And this is going to imply that C gamma F to the gamma minus 2 is also greater than 0. And again, this just comes from, well, I guess I'll say this comes from a combination of what we assumed and what we just figured out over here, okay? So if we know that this guy is greater than 0 and, if we know that this is greater than 0, this is greater than 0, and we want this to be less than 0, then I guess we need gamma minus 1 to be less than 0. So I'll just say, so gamma minus 1 needs to be, actually, write it like this. I'll say, so C gamma minus 1, F to the gamma minus 2 less than 0 implies gamma minus 1 needs to be less than 0. Or if you add 1 to both sides, gamma needs to be less than 1. And I'll use this guy right here. All right, so what are the conditions for gamma that satisfy x prime is greater than 0 and x double prime is less than 0? Gamma needs to be strictly between 0 and 1.